Hello everyone, welcome back to this channel. This is James. I'm a computer science graduate turned teacher, and in this video we're going to look into A-level computer science chapter 6 assembly language programming, and this is the chapter outlined. So without further ado, let's look into the first sub-chapter of this chapter. It's called machine code instruction. So what is machine code? If you look into this diagram here, machine code is essentially binary, 0 and 1, and it is the only language that the CPU recognizes, and it consists of a sequence of instruction. For example, I've color-coded this 1 and 0 here to represent how machine code can be used to represent instruction 1, instruction 2, and instruction 3. So every instruction here consists of two parts. The first part is what we call the opcode. Long term is for operational code. Whereas the second part of the instruction is called operands. So an instruction can have one or more operands. So these are some of the things that must be defined for a machine code instruction. So how many bits is in one instruction, and how many bits out of that it is used to define for opcode, and how many operands should we use, and whether the opcode is located at the most significant bit, which is the left hand side, or is it located at the least significant bit. So to help you visualize what is in one instruction, just think of it, as I said, there are two parts of the machine code. First part, opcode, usually stand for a verb, meaning an action that the computer do, an instruction, whereas operands is usually a data or an address. So this is how an instruction could be organized. So an example here is that 4 bits is used to define the operation, 2 bits is used for the address mode, another 2 bits is used for the register addressing, which these are the terms that we'll look into throughout the video, and operands 16 bits. So we have a register transfer notation here to just help people define that how the opcode of an instruction can be moved from the CIR, current instruction register, to the CU, control unit, to help the component identify what is the current instruction that is taking place now. So this is just machine code instruction, but the main topic for this video today is called assembly language. So let's discuss why is it needed. So sometimes a programmer may desire to create a program in which they have direct control over the actions executed by the processor. So for example, this programmer said, I want to add 5 to the ACC register, which is over here, accumulator. So this can be done in an assembly language, but it cannot be done if you're using a high-level programming language like Python. And it would be difficult to code in assembly language like 0 and 1 here. This is why we need assembly language to make it more human readable and writable. So assembly language is just a low-level programming language that uses symbolic instructions to represent the opcode and operands. So for example, the opcode and operands in a machine code would look like that. But it would be hard for us to code in this pattern, right? It's not readable. This is why they said that in assembly language, we use human readable word and mnemonics to represent the opcode and the operands. So this helps to, again, as stated, facilitating human readable coding closely linked to the hardware. And in order to convert assembly language to machine code eventually, because as I said, conversion is needed because this is the only language that a computer can understand. This is when the assembler comes in, a program that translates assembly language code into machine code. So these are some of the special features of an assembly language. They allow comments, which is code that is not run by the computer. It's just for programmers to know, oh, what this chunk of the code represents. Symbolic names for constant. I will show you what it means in a later part of the chapter. Labels for addresses. Macro. So macro here is a code snippet that can be reused to simplify and streamline programming tasks. So once you have written the macro, you can reuse in your program by just calling it. So you don't have to rewrite the code repeatedly. So directive. A directive in assembly language is a special command or instruction used to provide guidance to the assembler and define various aspects of the program structure, organization, and behavior. So now I'm going to show you how an assembly language would look like in order to help you understand what are the different features for an assembly language. So I'm gonna do it line by line to just prevent you from getting overwhelmed. So I have a program here that has around 15 lines, but I'm gonna show you a part in a time. So first line of the code stated int, just 2-character int. So this is the syntax for taking input from the users. A single number is input at the keyboard, and its ASCII code is stored in the accumulator. And then sub 48, so subs means subtract, the short form, the syntax. Convert this ASCII code into binary code for that number. So, and then you will store STO into the accumulator. And this value here is labeled as max. So by the way, this entire program will take in one number at the keyboard. So we'll only take single numbers input at the keyboard, and then for now, this input basically tells user how many numbers do you want to take in. So another part of the program, load 0 into the accumulator. You can see that this is how the feature of an assembly language. You can directly load in value that you want into a component in a CPU. So store it in total, at the address label total, store it in count, at the address label count. It's okay if you are not getting it now, just bear with me. I'll go through it step by step later. And then once you have gotten in the number that you want to take in, so the program will take in another input, subtract 48, and add it into the total, and store it in the total address. So we'll then load the value stored at the address count, meaning how many numbers are we taking, increment 1 to the accumulator, which is incrementing the count, and then we'll compare the max value that we have taken in the beginning, and it will jump. If they are not equal, then I will jump the instruction back to strltp. If not, the execution of the program will finish, and followed by the 3 variable that we have seen. So these are what we call the symbolic name, symbolic constant. So at this point, you might feel very confused. What are these things actually doing? So no worries, we are going to look into each instruction, what they do in a while. But in this slide here, I just want to show you how assembly language is like, and then how it can be used to put in a specific value into a register. All right. So there are 3 different ways we can write an assembly language code. So 3 different types of addressing mode: symbolic addressing, and absolute and relative. So I'm going to show you what symbolic addressing means first. So symbolic addressing is a method in which memory locations are referred to by labels or symbol. What it means here is that, look, after you take in a number, you subtract by 48, instead of saying, I want to store it in location 215, you gave it a label, max, to indicate that this is the address that stores the max value. So in other words, symbolic addressing make the code more human readable, with the actual address determined during assembly or linking. Meaning when you're writing the code, you don't have to care about the location on which the value is stored. So you don't have to remember that. And the other method is called absolute addressing. So this is slightly more complicated. Instead of just addressing using the label, you are using the exact memory address. So look, I have underlined the code, that part that has been changed. So instead of storing at max now, you're storing at location 215. So which essentially you're saying that you're storing at this exact location 215. So this is called absolute addressing, where you are writing the code in a way that specifies the exact location of the program. So the third type is called relative addressing, and this is a little bit more interesting. So look, before this, in absolute addressing, we're referring to the absolute address. But in relative addressing, it assumes that the program will start its address at 0, which is actually not the case, but then it just makes the programmer assume that every instruction, it will start from 0. And it's like a layer of abstraction so that the programmer doesn't have to remember the exact memory location. It specifies memory location based on their position relative to the current instruction or data, typically using offset or displacement. So if you can see here, instead of storing at 215, they have a BR here. BR stands for base register. It contains the base address. For example, it could be 200. in which the address is the address of the first instruction in the program. So if you are writing BR plus 15, essentially they are saying, I want this value to be stored at whatever location I'm starting plus 15, which is over here. So this is what we call relative addressing. So the three addressing mode: symbolic, absolute, and relative. So depending on how you want to write your program, there are three different choices. Right, so that's all about addressing. I know that you might feel very confused, but no worries, be patient with me. So let's look into the assembly process for a two-pass assembly. So basically, this section of the video explains how assembly code like that can be translated to binary code. So it's called, so a two-pass assembly is a type of assembly language assembly that processes the source code in two sequential passes, where the first pass gather information about labels and addresses, meaning they find out the offset of these labels. And the second pass will generate the machine code based on the assembly code written. So let me show you an example. So an assembler will usually do a pre-translation steps to eliminate comments, expand macro instruction into the individual instruction, and remove and store directive for later processing. So that's not even the first pass yet. So in the first pass, that means it will go through the entire code and then gather information about the address of the labels. So look, there are a few labels here: max, total, and count, and str, TLP. And then what it will do is that it will find the offset of it. And max, look, it is stored at location 215. So the offset of it is actually the difference between the actual location and also the base location. That's why it's called, they gather it as plus 15. Because if they don't go through the first pass, they cannot make the machine code for this instruction here. So this is why total is also gathered, count is also gathered. And that's the first part, to gather information about the addresses of the labels. And then the second part, they will use the symbol table, and which is this one that is generated, and the opcode lookup table. Look, the opcode, these are the opcode in, sub, store. And they assign this operational code with a binary, so that when the computer is processing this data, they know that this is the instruction for in, for instance. So there's another table to just store the binary for their symbols. So after that, after two passes, then they can use both tables to generate the machine code for the program. So in here, if we look into the opcode table, this is its binary. Therefore, in is being translated to this. And then sub 48. So first of all, we find out what is sub. Sub is this binary here, therefore it's over here. And then the last 16 numbers here is the operand. And then 48, so you can see that 110000 is actually the binary for 48. And followed by STO max. This is when the symbol table comes in. Max, it has been found that it's plus 15 offset. So this is why in the opcode section we use STO. So we basically move this to here. But the operand, we refer it to the symbol table. They found it as 15. So 15 will be written as the operand, and so on and so forth. So this is what a two-pass assembler do. The first pass, gather the information about addresses and labels of the labels, and then the second pass, look up the symbol table and the opcode lookup table to construct the machine code for the assembly language. So this is a two-pass assembly. The opcode, the operand, and then this is for certain instruction, just know that there's no opcode. Great, let's look into the fifth part of this video called the addressing mode. An addressing mode in computer programming specify how a computer references or access operands. So let me give you an example. So there are 4 different types of addressing mode, meaning how this operand is actually going to be useful. So the first type is called the immediate addressing. It represents the value that the instruction utilizes, the value that will be added. So 3 options for immediate addressing. If it's just hashtag 46, it directly specifies the binary value 46. But if you want to write the value in binary, you can just put a B in front of the hashtag. So that's the binary value for 46. And you can even use hexadecimal. So just put a and sign above your hashtag and then write down your hexadecimal value. So this is immediate addressing, meaning that you add this value directly to whatever thing, whatever register you are referring. Whereas direct addressing is slightly more complicated. This count here, add count, it's not a value, but then what it's saying is that the count label here contains the value that we need. So in other words, if you look into this example here, inside the count address, it contains the value 17. So this is equivalent to us saying, I want to add 17. All right, so that's direct addressing. Indirect addressing is even more complicated. So look, for indirect addressing, you have a square bracket. So instead of saying, I want to add whatever that is inside count, add 17, it's saying that whatever that is inside count, 17 here, is the address that we want to find our value in. So count contains 17. So this is the address we look up. So I'm going to go to 17. I found that the value 100 is inside. So in other words, this is equivalent to saying I want to add 100. The address that is inside count is useful for us to find the value. So that's indirect addressing, very indirect. Index addressing is an addressing technique in computer programming where an index or offset is added to a base address to access a specific memory location. So add 17 here, is index addressing basically mean I look into what is inside my index register. I add it with 17. So 17 plus 2 will be 19. So I'm going to go to address 19 and find out the value. In other words, add 17 here is equivalent to adding 300, right? So it involves looking up whatever that is inside the index register. So now is the gist of this lesson here. So far we have seen the different instruction, the opcode, but what do they actually mean? What's the difference between ADD and STO and even LDI? So I'm gonna explain it in a very easy way to help you understand the different instruction in an assembly language. So the first type of instruction is the data movement instruction. So we have a few instructions on data movement, all right? LDM, immediate addressing, LDR, immediate addressing, but instead of loading the value to ACC, it's loading it to index register. LDD, direct addressing, load the content at a given address to ACC. So there are multiple instructions here. So I'm going to show you one by one in an image what each instruction do. So LDD 19, if we read the instruction, is direct addressing, load the contents at the given address to ACC. So 19 here is the given address, and 300 is inside address 19. In other words, I'm saying that I want to load 300 at address 19 and to my accumulator. So that's what LDD do, direct addressing. Whereas you can also put a label here. So previously we put a number, an address, but then you can also put a label here as your operand. Basically, I'm saying I want to load the value that is inside max 999 into my accumulator. So that's two ways you can use it. LDI, the I here stands for indirect, LDI 20. So if I write this instruction, I'm going to look into what is inside address 20 and then use the value here as my address to find the value I want, which is 17. So I'm going to go to 17 and find the value 100 and load it into the accumulator. So you can see that it's not very straightforward. That's why it's called indirect addressing. STO 18, so basically STO stands for store, the short form. It stores the content of ACC into address 18. So if my ACC contains 100, then I'll put this value into address number 18. MOV-IX, move the contents of ACC into IX. So it doesn't even have to be IX, it can be any register because that's the syntax. So ACC is 10, so I basically move this value into my IX. LDX 10, index addressing. So for, basically what it does is that, look, LDX 9, so I will find out what is inside my index register, 10, add this up with my operand. So 10 plus 9 is 19, which means I need to load the value in address 19 all the way to accumulator. And this is the description. You can read it yourself. So this is the first type of instruction. Let's do the second type of instruction, input and output. In my opinion, they are the most straightforward. In takes in a value. The ASCII value of a character type at the keyboard will be stored in the accumulator. Whereas out, show on the screen the character corresponding to the ASCII code. Basically just input and output thing. And there's not much explanation on this. And the third types of instruction is the comparison and jump. This is very important because it gives the program a lot of flexibility. So let me explain it in this manner, instruction by instruction. JMP here stands for jump, and it jumps to the given address. So if you remember, in the last chapter, we learned that PC, the program counter of a CPU, gives you the address of the next instruction that we'll be executing. So if you use the instruction JMP 200, essentially you are overriding the current value of PC to 200. So you are essentially telling the program in the next instruction, instead of executing the instruction at location 17, I want you to execute the instruction located at 200. You're jumping an instruction. So after you jump, there's another thing called comparison. CMP, compare the content of ACC with the contents of address. So CMP 19 means that I compare the content in 19, 300, with the accumulator. And once this comparison is done, depending on the result, I will store the flag bit into the SR, status register. So this, in this chapter, you can see how different registers are useful. CMP 300, so instead of comparing with a value in an address, you can also compare directly with a value instead. CMI, indirect addressing. Again, every time you see an I, is something very indirect. The logic is the same as LDI. So I look into whatever that is inside address 200, and I'll find the address that I actually care about. So I'm going to go to 18 and compare my accumulator with whatever that's inside address 18. So you can see that if they are not equal, 0 is stored in the status register instead. So what is so important about the CMI is that it allows the program to jump into a specific part of the code depending on some condition. Look, after a compare instruction, your status register is going to contain either 0 or 1 to show the result of the comparison. And this is when JPE and JPN comes in. So JPE, it will jump to address if the compare was true. So JPE 200 jumps to 200 if the status flag is true. So before the comparison, before the jump, so I can see that SR contains a value 1, meaning true. So because of this, when I use this instruction, my PC will be changed to 200. So this is what compare and jump mean. So JPN is the opposite. It will only jump if the comparison was false. So if you look at it, my SR is 0, so I'm going to jump to 200 after that. So this is compare and jump instruction. They might not look very useful individually, but if you use them in an assembly language programming, it'll be very, very useful, in which we'll look into in chapter 20 plus, I believe. So for now, it's just an introduction. Arithmetic, basically adding, subtracting, incrementing, and decrementing. So let's look into one example to just use all the instruction up, adding. So let's say I LDD 19, basically I load whatever is inside 19 into my accumulator. Let's say I want to add this value. I can just use the instruction. Either I can add a direct number. So before this is 300, add 100, the SAC becomes 400. And add 200, look, this one doesn't have a hashtag, meaning I'm adding the value inside address 200, which is 18. So this is why you can see 400, after you add 18, you got 418. So this is basically just some example of how to use the arithmetic operation. So the shift operation is special. It's also related to arithmetic, but then we use it for multiplying and dividing. So let me explain. Before I show you what this instruction is useful, you need to understand what is logical shift. So for an unsigned integer, logical shift is an easy way to multiply and divide a number. Look, 110 binary is equivalent to 6 in binary. But then if you were to left shift each bit one time, you'll get 1100. And if you calculate the denary value of it, it has become 12. In other words, this concept says that if you left shift all your bits by one place, you are multiplying your value of the binary by 2. So that's left shifting. And then if you right shift it, you will get the opposite. So 110, if you right shift it, you get 11, in which is 3 in denary. So you are essentially dividing the number by 2. So that's logical shift. But for certain example, like signed integer, what we learned in chapter 1, the first bit is used to represent whether they're negative or positive. So operation may produce a result when a sign of the number has changed. So in this example, if we were to right shift a signed number, you'll find that, hey, before this is -6. But after you right shift it, instead of dividing the number by 2, the value is now incorrect because the sign bit has been moved. So it doesn't really work that well for logical shift for signed integer. But of course, there's a solution to this. You can either use arithmetic logic shift, meaning I retain the sign bit and then you only move the other bits. So this is when right shift will move for it, considering that overflowing problem is not occurring. So another way you can do it is that you can do a cyclic shift. So instead of just deleting the bit, you're moving the rightmost bit to the leftmost bit. So this is what we call a cyclic shift. So this is why when this instruction comes in handy, LSL and LSR, so you're essentially shifting the bit inside a register to allow multiplication and division. So hopefully this explains it. So the last one is bitwise logic operation. In fact, we won't do a lot of example on this first. But if you remember, this verb here, it also appeared in our logic gates chapter. So basically what it does is that it's an bitwise AND operation, and it compare value in ACC and binary number n, and then use it to determine what the result is using the AND operator. Same goes to the XOR and the OR operator. So we are either comparing with a value, direct value, or a value inside the address. So depending on what mode you want to do in your program. So that's all the instructions. We're not in the phase of writing it out yet, but then this chapter is all about helping you to understand what each instruction means. Okay. So further consideration, computer arithmetic. So something the status register do. In the previous example, we see that it only stores 0 and 1 based on the comparison instruction. But it can also use to identify a specific overflow condition. So whether there is a carry in an operation, whether it is a negative value, whether an overflow also happens. So let me give you an example of what I mean. So consider adding 2 positive 2 complement number here. And after the operation, your computer might need to know whether overflow problem has occurred, whether it's a negative number. So we need the status register to detect this impossibility. So like in this example, we have an impossibility. When you add these 2 numbers up, you shouldn't get a -82. So look, because carry is involved, my status register is stored to 1 and then n. And because you see 1 here is at the most significant bit, meaning we have a signed integer, meaning which is not possible. So I set the negative flag to 1, and then 1, I also set the overflow register to 1 in order to find that, oh, this actually the overflow problem has occurred. All right, so the maximum value that an 8-bit 2 complement can store is 127. All right, so that's about it. The last part of the chapter, which is also a frequently asked exam question. How do we track the value stored at each location throughout the assembly program? So what I have here on my left hand side is the program, and the right hand side is the trace table that you can use it to track the value stored in each location. It can be either a register or a memory location. So let's go through this program one by one. This program will take in 3 inputs and add the result by 100. And by using a trace table, we can track the value at each state. So the first step, in 75, because the first input is 75, so it will store the input value to 75. And then STO 900, meaning I will store whatever value inside accumulator into memory location 900. So they will take in another input, 92, store it at 901 instead, and take in another input, and then add 900. Remember, I'm not adding the number 900, but whatever that is inside memory location 900. So 87 will be added to 162 after adding 75. So add 901, I add value inside 901, and then add 100. So if you look at this hashtag, is actually adding the number 100. I got 354, and then output, so 354, and then the program is ended. So this is something that you need to do for your exam. So they're going to show you a trace table and ask you to track the value of each location at each stage of the program. So in order to teach you better, I have another example here with another program. So let's start with LDD201. But before that, you can see that at each location, 201 to 204, they all have different values, which is why I initialize it here. So LDD201, direct addressing, load whatever that is inside 201 into accumulator. INC ACC, remember INC will only increment the accumulator by 1. STO 202, basically I store whatever is inside accumulator in address 202. LDI 203, so this is special because I'm not loading whatever value that's inside 203, but this is an indirect addressing, so I look up whatever value here, and this will be the address that I use to get my value. So this is why I load 5 into the accumulator instead. So DEC ACC, meaning I'm decremented by 1, store it inside 201, and add whatever that is inside 204. So add 204, meaning I add whatever value here, 5, to my accumulator, 4, so I get 9, and I will store this value into 201. And then the program is ended. So it's pretty easy if you understand what each instruction do. This is why in the beginning of the video, I show you how each opcode behave, so that if you can remember, let's say, what LDI do, you can fill up the trace table pretty effortlessly. So that's pretty much the end of it. Thank you so much for watching until this part of the video. Let me know in the comment section if you have any question, and I'll be happy to help. Thank you for watching. See you.